Ton 618, the largest black hole ever discovered. There is something out there, something so massive, so incomprehensibly large, that if you placed our entire solar system inside it, we would be lost, invisible, a speck of dust in a cathedral. It sits at the edge of the observable universe, billions of light years away, devouring stars, warping spacetime, shining brighter than 1,000,000,000,000 suns combined. Its name is Ton 618, and it is the largest black hole we have ever found. To understand what Ton 618 is, you need to forget everything you think you know about size. Forget the Sun, forget Jupiter, forget the distance from Earth to Neptune. Those scales are meaningless here. TON 618 operates on a level that the human mind cannot naturally comprehend, a scale where numbers stop making sense and only comparisons remain. Imagine standing on Earth and looking up at the Sun. It's 93 million miles away, yet it dominates the sky. Its light warms your face. Its gravity holds planets in orbit. It contains 99.86% of all the mass in our solar system. The Sun is massive, powerful, the anchor of everything we know. Now imagine something 66 billion times more massive. Not 66 million, not 66,000, 66 billion. The number itself is almost meaningless. Your brain can't process it in any intuitive way. But here's what it means in practical terms. If you could somehow gather 66 billion copies of our Sun and compress them all into a single point, you would have Ton 618. But even that comparison fails to capture the reality. Because Ton 618 isn't just massive in terms of weight, it's massive in terms of space, in terms of the region of space-time it controls, in terms of the event horizon that marks its boundary of no return. TON 618 is a quasar, an extremely luminous active galactic nucleus powered by a supermassive black hole consuming matter at the center of a distant galaxy. It was discovered in 1957 during the Tonensintla Observatory Survey, a photographic survey of the sky searching for faint blue stars. Astronomers noticed an unusual object, blue, bright for its apparent size. But when they measured its spectrum, they realized it wasn't a star. The light was redshifted, dramatically redshifted, which meant it was far away, unimaginably far away. It sits in the constellation Canes Venatici, the hunting dogs, a small constellation in the northern sky. From our perspective, Ton 618 appears as nothing more than a faint point of light. You couldn't see it with the naked eye. You'd need a powerful telescope. And even then, it would look unremarkable, just another dim speck among billions. But that speck is 18.2 billion light-years away. Let that distance sink in. Light from Ton 618 has been traveling toward us for over 18 billion years. It left Ton 618 when the universe was less than 1 billion years old, when galaxies were still forming, when the first stars were igniting, when the cosmic dark ages were ending, and light was beginning to illuminate the universe for the first time. Earth didn't exist yet. Our Sun didn't exist. The Milky Way was a chaotic cloud of gas, not yet settled into the spiral structure we see today. And Ton 618 was already there, already massive, already feeding, already shining across the cosmos with a luminosity that defies comprehension. The light we see now is ancient, a fossil, a message from the early universe, and it tells us something disturbing. Supermassive black holes grew much faster than we thought possible. But before we can understand why Ton 618 is a problem for astrophysics, we need to understand what we're looking at. When you observe a quasar, you're not seeing the black hole itself. Black holes emit no light. They are by definition black, invisible. What you're seeing is the accretion disk, the swirling maelstrom of matter falling into the black hole. As gas, dust, and torn-apart stars spiral inward, they accelerate faster and faster, approaching significant fractions of the speed of light. The material collides. Friction heats it to millions of degrees. The disk glows, radiates. The inner regions, closest to the event horizon, reach temperatures so extreme that they emit X-rays and gamma rays. Farther out, the temperature drops, and the disk emits visible light and infrared. And because the black hole is so massive, there's an enormous amount of material falling in. The gravitational pull extends for thousands of light years. Gas clouds are drawn in. Stars wander too close and are shredded by tidal forces, their matter funneled into the accretion disk. The disk is vast, hot, turbulent, chaotic. Magnetic fields thread through it, channeling energy, launching jets of plasma perpendicular to the disk at velocities approaching the speed of light. These jets are one of the most powerful phenomena in the universe. They extend for hundreds of thousands of light years, millions of light years in some cases, carving through intergalactic space, heating gas, preventing star formation, shaping the evolution of galaxies. The energy output from a quasar jet can exceed the total luminosity of 1 trillion stars. TON 618 is what astronomers call a hyperluminous quasar. It shines with the brightness of 140 trillion suns, not billion, trillion. To put that in perspective, the Milky Way galaxy, which contains between 200 and 400 billion stars, has a total luminosity equivalent to about 20 billion suns. TON 618, a single object, outshines 7,000 galaxies the size of the Milky Way combined. If TON 618 were placed at the center of the Milky Way, replacing our relatively quiet supermassive black hole Sagittarius A star, the sky would be blindingly bright. The accretion disk would outshine every star in the galaxy. Night would cease to exist. The entire sky would glow with a searing blue-white light. Radiation would sterilize the surface of Earth. The atmosphere would be stripped away. Life would be impossible anywhere in the galaxy. But TON 618 isn't here. It's 18.2 billion light years away. So far that the light has been traveling longer than the age of Earth. So far that the expansion of the universe has stretched that light, redshifting it, lowering its energy, making it detectable, but not dangerous. Yet even from that distance, we can measure it. We can calculate its mass. We can estimate the size of its event horizon. And those calculations reveal something almost obscene in its scale. The event horizon of a black hole is determined by its mass. It's the boundary where the escape velocity equals the speed of light. Inside the event horizon, not even light can escape. The more massive the black hole, the larger the event horizon. For a stellar mass black hole, one formed from the collapse of a massive star, the event horizon might be a few kilometers across. For Sagittarius A star, the E1 supermassive black hole at the center of the Milky Way, with a mass of about 4 million suns, the event horizon has a radius of about 12 million kilometers. TON 618, with a mass of 66 billion solar masses, has an event horizon with a radius of approximately 1,300 astronomical units. 1 AU is the distance from Earth to the Sun, about 150 million kilometers, 93 million miles. So the event horizon of TON 618 has a diameter of 2,600 astronomical units. To put that in perspective, Neptune orbits the Sun at about 30 astronomical units. Pluto's orbit varies between 30 and 49 astronomical units. The Kuiper Belt, the region of icy bodies beyond Neptune, extends to about 50 astronomical units. The scattered disk, where objects have highly elliptical orbits, reaches out to about 100 astronomical units. Even the Oort cloud, the distant shell of icy comets that marks the outermost boundary of the Sun's gravitational influence, only begins at around 2,000 astronomical units and extends to perhaps 100,000 astronomical units. The event horizon of TON 618 would reach into the inner Oort cloud. Everything inside that radius would be beyond the point of no return. Our Sun, all the planets, the asteroid belt, the Kuiper Belt, everything humanity has ever known or explored. All of it would be inside the event horizon of TON 618, trapped, falling toward the singularity. And this is just the event horizon, not the black hole itself. The singularity at the center, where all 66 billion solar masses are theoretically concentrated, is infinitely small. A point, zero volume, infinite density, a place where mathematics breaks down and produces results that make no sense. How does something like this form? How do you build a black hole this massive? The process begins billions of years ago in the early universe. Shortly after the Big Bang, the universe was hot, dense, uniform, but not perfectly uniform. There were tiny fluctuations, regions where matter was slightly denser, and gravity amplifies differences. The denser regions pulled in more matter. They grew. Over millions of years, these density fluctuations collapsed into the first structures: dark matter halos, gas clouds, protogalaxies. In the centers of these protogalaxies, conditions were extreme. Gas was dense, collisions were frequent, and in some cases, something formed that would become the seed of a supermassive black hole. There are several theories about how these seeds form. One possibility is that they start as population 3 stars, the first generation of stars in the universe. These stars form from primordial gas, hydrogen and helium with trace amounts of lithium. No heavier elements, no metals in astronomical terms. Without metals, the gas couldn't cool efficiently, and without efficient cooling, it couldn't fragment into small clumps. So the first stars were massive, tens or hundreds of times the mass of the sun. Maybe more. These stars burned hot and fast. Their lifetimes were measured in millions of years, not billions. And when they died, they didn't fade quietly. They exploded as supernovae, or, if massive enough, collapsed directly into black holes. Black holes with masses of tens to hundreds of solar masses. These could have been the seeds, starting points for supermassive black holes. But growing from 100 solar masses to 66 billion solar masses takes time. A lot of time. And there's a limit to how fast a black hole can grow. When a black hole feeds, the infalling matter heats up and radiates energy. This radiation exerts pressure, outward pressure. At some point, the radiation pressure balances the inward pull of gravity. This is called the Eddington limit. If a black hole tries to feed faster than the Eddington limit, the radiation blows away the infalling matter. The black hole chokes on its own food. For a black hole to grow from stellar mass to supermassive scales, feeding at the Eddington limit, it takes billions of years. Time for the black hole to slowly, steadily consume gas and merge with other black holes. Time for the accretion disk to feed it. Time for the host galaxy to funnel material into the center. But TON 618 existed when the universe was less than 1 billion years old. There wasn't enough time. Even if a population 3 black holes started feeding immediately, at the maximum rate, it couldn't grow to 66 billion solar masses that quickly. The timeline doesn't work. This has led to alternative theories. Maybe the seeds weren't stellar mass black holes. Maybe they were more massive from the start, direct collapse black holes. In the early universe, under specific conditions, a massive gas cloud could collapse directly into a black hole without forming a star first. This process could create black holes with masses of thousands or even millions of solar masses. Intermediate mass black holes. These larger seeds would have a head start. More mass means more gravity. More gravity means faster feeding. Given 1 million solar mass seed in 1 billion years, you might be able to grow something as large as TON 618. Or maybe black holes in the early universe fed faster than the Eddington limit. Maybe the conditions were different. Denser gas, more chaotic dynamics, frequent mergers with other black holes. In the crowded, violent early universe, black holes might have had access to more food and fewer barriers to growth. Or maybe we're missing something, some mechanism we don't understand, some process that allows black holes to grow faster than our models predict. TON 618 is evidence that we don't have the full picture. It shouldn't exist according to our current understanding, but it does, and that means something is wrong with the models. This is one of the great unsolved problems in astrophysics. How do supermassive black holes grow so large so quickly? And it's not just TON 618. Other ultramassive black holes have been found in the early universe. SDSSJ 0100113.02 plus 280.225.8, a black hole with a mass of 12 billion solar masses, existed when the universe was only 900 million years old. Phoenix A, a black hole with an estimated mass of 100 billion solar masses. though this estimate is controversial and possibly overestimated. Home 15A, with a mass of 40 billion solar masses. Each of these discoveries forces us to reconsider our assumptions, to revise our models, to accept that the early universe was stranger and more extreme than we thought. But TON 618 remains the most massive confirmed supermassive black hole, and it raises another question. Could there be something even larger? Theoretically, there's no hard upper limit to the mass of a black hole. If a black hole has enough matter to consume, it can keep growing. But practically, there are constraints. Galaxies only have so much gas, so many stars. At some point, a black hole consumes or ejects everything nearby. The surrounding region becomes depleted. The black hole starves. Additionally, as a black hole grows, its energy output increases. A more massive black hole has a larger accretion disk, more infalling matter, more radiation, more powerful jets. These jets and winds can blow gas out of the galaxy entirely, preventing it from falling into the black hole. This is called AGN feedback, active galactic nucleus feedback, and it's a self-regulating process. The black hole limits its own growth by destroying its food supply. Current theoretical models suggest an upper limit somewhere between 100 and 270 billion solar masses. The exact number depends on assumptions about galaxy formation, gas supply, and accretion efficiency. TON 618, at 66 billion solar masses, is already 2/3 of the way to the upper theoretical limit. If something larger exists, it would be extraordinarily rare. We've surveyed billions of galaxies, observed thousands of quasars. TON 618 is the largest we've found. Either it's truly the largest, or larger black holes are hidden in regions of the universe we haven't surveyed yet. Or they exist at distances so extreme that their light hasn't reached us yet. Or perhaps they existed in the past but have since merged or stopped feeding, becoming quiet, invisible giants lurking in the centers of galaxies. We may never know. The universe is vast, and our observations are limited. But for now, TON 618 holds the record, the largest black hole ever discovered, a monument to extremes. Now imagine what it would be like to approach TON 618. Not that you could survive the journey. The radiation alone would kill you long before you got close. But in a thought experiment, protected by some impossible technology, what would you see? From a distance, TON 618 would be invisible. The black hole itself emits no light, but the accretion disk would be a blazing beacon, a disk of superheated gas spanning thousands of astronomical units, glowing with the intensity of 140 trillion suns. It would dominate the sky, blinding. The light would be blue shifted on the side rotating toward you, red shifted on the side rotating away. Doppler shifting visible in real time. As you got closer, space-time itself would begin to warp. General relativity predicts that massive objects bend space-time around them. The more massive the object, the more severe the curvature. Near TON 618, space-time is bent to an extreme degree. Light from distant stars would curve around the black hole. You'd see stars that are actually behind the black hole appear in front of it. Gravitational lensing. The sky would be distorted, warped into arcs and circles, and time would slow down. Clocks near TON 618 would tick slower than clocks far away. This is time dilation, another prediction of general relativity. The stronger the gravitational field, the slower time moves. If you were orbiting just outside the event horizon and looked back at the universe, you'd see everything speeding up. Stars would be born and die in moments. Galaxies would collide. The universe would age before your eyes, but you couldn't orbit there for long. Tidal forces would be immense. Even though TON 618 is so massive that its event horizon is relatively gentle, the difference in gravitational pull between your head and feet would eventually become extreme. The closer you got to the singularity, the stronger the tidal forces. Your body would stretch, elongate. Atoms would separate. You'd be spaghettified, torn apart into a stream of particles spiraling down into the abyss. And once you cross the event horizon, there would be no escape. Not because the black hole is pulling you, but because space-time itself is so warped that all paths lead inward. You couldn't turn around. You couldn't fire rockets. Inside the event horizon, forward in space is the same as forward in time. And time only moves in one direction, toward the singularity. How long would it take to reach the singularity? From your perspective, not long. Minutes, maybe hours depending on your trajectory. But the experience would be strange, disorienting. You'd see the universe behind you compressed into a shrinking circle of light. Blue shifted, brighter. The rest of the sky would be dark. Ahead of you, nothing. Just the inevitable pull of the singularity. And then, at the center, you'd encounter something that shouldn't exist. A point where all the mass is concentrated, where density becomes infinite, where the curvature of space-time becomes infinite, where the equations of general relativity break down and produce infinities. Nonsense. Physicists hate infinities. They're a sign that the theory is incomplete, that something is missing. We think that quantum mechanics, the physics of the very small, must play a role at the singularity, that quantum effects prevent true infinite density. But we don't have a theory of quantum gravity. We don't know what happens at the Planck scale, where quantum effects and gravitational effects are equally strong. So the singularity remains a mystery, hidden behind the event horizon, unobservable, unknowable, a place where physics ends and speculation begins. Ton 618 is a reminder of how little we understand. We can measure it, observe it, calculate its properties, but we can't explain it, not fully. We don't know how it grew so fast. We don't know if it's still growing. We don't know what lies at its center. We don't even know if it's the largest black hole that exists, and maybe we never will. Because Ton 618 is 18.2 billion light years away. The universe is expanding, space itself is stretching, and Ton 618 is receding from us faster than we can ever reach it. Even if we could travel at the speed of light, we could never arrive. The expansion would carry it away faster than we could approach. We are observers, witnesses to a cosmic extreme. We can see it, study it, marvel at it, but we can never touch it, never visit it, never truly understand what it means to stand at the edge of something so massive, so powerful, so fundamentally incomprehensible. Ton 618 exists at the boundary of human knowledge, where our theories struggle, where our intuition fails, where the universe reveals its capacity for extremes that make everything we know seem small and fragile and temporary. It is the largest black hole we have ever found, and it will remain out there, billions of light years away, feeding, growing, warping space-time, long after humanity is gone, long after Earth is dust, long after the sun has exhausted its fuel and collapsed into a white dwarf. Ton 618 will endure, a colossus, a titan, a monument to the universe's ability to create things beyond comprehension, and a reminder that we are very, very small.